Hello and welcome to AP Biology, and as we wrap up our kind of review of chemistry that we did with our summer homework and a little bit in class, we're going to go right into the kind of the chemistry of water, which will lead to pH, so that we can look at water, look at how its chemistry impacts living things, and look at its importance to living things around the world. So the first thing to know about the water molecule is it's a polar molecule. So what that means is there's a partial separation of charges. So if you look at the diagram in the upper right-hand corner here, you will see that the hydrogens and oxygen, they're sharing electrons. They're sharing right here and right here. But oxygen has something that's called really high electronegativity, and because of that, they're going to hog the electrons. The electrons are going to be pulled towards the oxygen, and because of that, the electrons spend more time around the oxygen, and it takes on a negative charge, and the hydrogens are left with a positive. So that's a polar molecule. There's a positive and negative end to it. And because of the polarity of water, it gives it four main properties that we're going to talk about. So the first one is this idea that water is cohesive. It sticks to itself, and related to that is also this idea of adhesion. It sticks to other substances. And I guess I should say other polar substances. The second thing, it stabilizes or moderates temperature. It's got a high heat capacity, so it acts as a heat sink. It has to absorb a lot of energy before it changes temperature or changes state. Number three, it expands when it freezes. It's the only substance that we know that does that, so that the solid actually floats on top of the liquid phase of it. And then finally, water is often called the universal solvent. And when we get into the circulatory system and talk about our blood, which is mostly water, it's going to be very important that it acts as a good solvent. So here's what we mean about water being a polar molecule. So again, if you look at the blue electrons right here and here, those are being shared between the oxygen and the hydrogen, but because the oxygen has a higher electronegativity, it's going to hog the electrons, if you will. So the electrons are pulled towards the oxygen. It gives it what's called a partial negative sign, and the hydrogens are left with a partial positive. So this little symbol that we see here means partial. So there's not a complete separation of charges like we might see in an ionic compound. So water's covalent, but it's a polar covalent because there's a separation of charges where the electrons are unequally shared. And so here is just a quick table. You can look at it and kind of goes over the properties of water that we just said. So the first two are kind of combined. They resist changes in state and temperature. Here it acts as a universal solvent, is cohesive and adhesive, has a high surface tension, which plays right into cohesion and adhesion, and it's less dense as ice than liquid. So you can pause it if you want, get that table down, but just another way to look at the properties we're going to be talking about. And so when we talk about it, I mentioned before, it's a covalent bond. So here's a Lewis dot structure over here that shows on the left, that shows how the electrons are being shared. So hydrogen with its one valence electron isn't stable. It would like to get two valence electrons. And oxygen with its 6 blue valence electrons isn't stable. It would like to gain 2 more. So 2 hydrogens provide the extra 2 electrons. They share them, so that's the definition of a covalent, cooperative valence electrons, and we get H2O. And as that happens, over on the right, you'll see there's 3 water molecules there that are all shown as polar. They've got partial positive and negative charge. And what can happen is now when these polar water molecules get together, they can actually line up almost head to tail, right like that. And what will happen is in between them, from the positive to the negative, right like that, you'll get a hydrogen bond. So right here and right here is a hydrogen bond. And that's what holds the water molecules together and gives it the properties that we're going to talk about. Water kind of sounds weird to say it, but water at the molecular level is sticky. They want to be near each other. They're hard to pull apart because of these hydrogen bonds that hold them together. And here's what happens when there are 5 of them together. So we see the central water molecule here in the middle, and there are 4 hydrogen bonds that it makes with 4 water molecules around them. And all of these hydrogen bonds have a little bit of stick, and those water molecules are harder to pull apart than we might expect. So the first property we talked about real quick is cohesion. So this is water to water, and it's caused by hydrogen bonding. So they last less than a trillionth of a second, but they still give a little bit of cohesion, a little bit of attractiveness to them. And so the more water's more structured than most liquids. It sticks together more. And the same thing is true of adhesion, that if you've ever seen a graduated cylinder like over on the left here, we'll get a meniscus. The water won't go straight across. It kind of goes up on the sides, and that leads to surface tension. So if you've ever seen a water strider on a pond or something, it's kind of like us walking on a trampoline. It's not heavy enough to break the hydrogen bonds, so its legs push the water down and it can stride across the surface of them. And don't try this, but if you could ever take a water strider and put it in rubbing alcohol or ethyl alcohol or something like that, it'll go right in. There's not enough surface tension with those liquids to keep the water strider on top. So here's an example that we may actually do in class. If you've ever tried to see how many drops of water you can place on a penny, you will see the properties of cohesion and adhesion in place. And looking at it from the side in this diagram over here on the right, you can see kind of the green bonds down at the bottom, the penny, and there is adhesion between the solid penny and the liquid water. But then there's also cohesion within the bubble of the water on the surface that keeps it together, and you can actually have the water kind of seeming to bulge right over the edge of the penny. So there's cohesion and adhesion. The second one is water moderates temperature. Okay, so it mitigates changes in temperature because it acts like a heat sink. So anytime you've got 2 objects of different temperature, heat will always flow from the warmer to the cooler object. And when we look at something called the specific heat for water, this is the amount of heat absorbed or lost to change 1 gram of a substance 1 degree Celsius. So that's just to kind of standardize it. And if you look at water, the specific heat of water is 1 calorie per gram per degree Celsius. So it takes 1 calorie of energy to change 1 gram 1 degree Celsius. And this is due to the hydrogen bond that keeps those water molecules together. Now if we look at a similar liquid, ethyl alcohol, its specific heat is 60% of that. It's 0.6 calories. So it takes a lot less heat to break the bonds between those ethyl alcohol and evaporate it. And if you've ever spilled gasoline or rubbing alcohol or the rubbing alcohol pads from a shot at the doctor's office, it feels cool on your skin because it's evaporating very, very quickly and taking the heat with it. So here's a good table. You might want to pause the video for a second and look at it while I talk or before I start talking. But if you look here, if we can see down here at the bottom, here's water. And we can see, compared to these other liquids that are similar in terms of their molecular weight and such, it has a very high boiling point, almost double what acetone is. And the reason for that is as we try to boil it, as we try to evaporate it, the water molecules, the hydrogen bonds, are making it harder to pull apart. We have to put more energy into that. So the heat of vaporization, it takes over 2,000 joules per gram to evaporate water, whereas acetone, it's down near 500. So you can see the huge difference that the hydrogen bonding makes in the properties of water and how this can contribute to life in helping with homeostasis and helping maintain a relatively even body temperature. And this is evaporative cooling. Exactly what we want to talk about here is how the molecules move fast enough to overcome attraction to others. So what happens is down here on the bottom, so when we sweat, water's put on the skin, and it's the hottest molecules. They're the ones that get enough energy to actually change state and go into a vapor. They evaporate, so when they leave, they take heat with them, and the coolest molecules are the ones that left behind. So that's why when we sweat, it cools us down. And again, due to hydrogen bonding. So you can see here how the hydrogen bonds between the different water molecules will cause them to kind of stick together, if you will. And number 3, ice floats. So water is less dense as a solid. It's the only substance that we know that does that. So above 4 degrees Celsius, it contracts as it cools. It acts just like every other substance we know. It gets smaller, it shrinks. But at about 0 degrees Celsius, the water molecules form a lattice with 4 other water molecules, and it kind of pushes them apart and it keeps them at a distance. So all of a sudden, the density drops a little bit and the ice floats. And if ice were to sink, it would be catastrophic because lakes and ponds would freeze solid and kill all the life with them during the winter. And here's a quick picture that just shows how on the left-hand side, the ice, the hydrogen bonds are stable, but they're actually a little bit further apart than they are when they're liquid, and that's why it floats. Here's another diagram that shows the same thing. So if we look at the warm water, as we go from warm to cold water, it behaves like it's supposed to. The kinetic energy is reduced, the molecules go closer together, and they're packed in. And if you've ever been in a lake or a pond where you dive down deeper, you may have hit what's called the thermocline, and all of a sudden the water gets colder. And that's exactly what happens as the molecules lose energy, they get closer. But then all of a sudden, right around 4 degrees Celsius or so, boom, they break into this lattice, it becomes ice, and the ice rises to the surface because it's less dense. And the last one that we're going to do quickly here is water is often described as being the universal solvent. It's a dissolving agent. So the solute is the substance that is dissolved, like salt or sugar, glucose we'll talk about a fair amount, carbon dioxide in the blood. But if water is the solvent, it's called an aqueous solution. And because water is a polar molecule, it will surround ions like sodium, which is a positive cation, chloride, which is a negative anion, and it will separate them. That's why salt dissolves in water. And here's a picture of it here, and it actually forms these things called hydration shells. So it forms little bubbles of water around those ions. So if we put a chunk of salt in water, the water actually worms its way in between because of its polarity, and it surrounds the chloride, the negative ion, the sodium ion, here the positive, and keeps them separated, and that's why water acts as such a great solvent for that. And here's another diagram that shows a little bit better with the actual water molecules here with the hydrogens in white, right there, red now that I colored it in, and the oxygens in red. So the hydrogens, because they're partially positive, will always be attracted to the negative ion. The oxygen, because it's partially negative, will be attracted to the positive ion, and it will break up the solid sodium chloride and dissolve it. And that's why water works as a solvent, and those are the 4 main properties of water that we're going to be dealing with and why they're so important to life as we move forward in AP Bio. Thanks for your time.